Ladies and gentlemen, thank you for coming here today and welcome to Burlington House. First of all, a special thank you to Dr. David Giles for agreeing to do this talk, but also a special thank you to our sponsors, Soil Consultants, and to the Geological Society for the use of Burlington House. A bit about Dr. David Giles. He has over 30 years' experience in academia and industry, and as some of you will know, has been teaching in Portsmouth since 1991. David's expertise includes glacial and periglacial engineering geology, engineering geomorphology, landslides and slope stability, hazard and risk, just to name a few. David is also an active member of the Geological Society of London and a scrutineer for chartered geologists applicants. Today, he will be giving us a talk on engineering geology and geomorphology of glaciated and periglaciated terrains. Over to you.
Okay, it sounds terrible when you hear 30 years and you think you've only just started, so it's a sort of frightening figure. Thank you very much for inviting me this evening. I'm of a certain age that home counties north sends a shudder through the spine, which usually means sitting on Friday night watching Come Dancing when it was in black and white. So I always remember how times have changed. What I'm going to talk to you about this evening is firstly on some of the work that we've been doing in the engineering group. We've had a working party over the last 5, 6, 7 years, where we started to look at all aspects of the Quaternary in terms of what it means in terms of ground engineering, and particularly in terms of the construction of ground models for the reduction of engineering risk. So I'm going to talk a little bit in general about ground models, talk a little bit about some of the key issues in terms of the Quaternary, and then I'm afraid I'm going to sell you a book. So part of the output from the working party was the most recent engineering group special publication, Engineering, Geology and Geomorphology of Glaciated and Periglaciated Terrains. And this really was a sort of distillation of this knowledge, hopefully, with a currency and what will have hopefully an impact in the ground engineering industry. So I'm going to talk a little bit about the significance of the Quaternary to engineering geology, often overlooked. Many of you sitting in the audience would have done a geology degree, a pure geology degree, and the Quaternary was seen as something you grew potatoes in. It wasn't seen as something as anything that was significant. And yet, as we'll see, hopefully we'll see that if you're working in any environment, whether it be petroleum, engineering, geology, civil engineering, minerals exploration, you go through the Quaternary, you go through Quaternary deposits. And understanding that the significance of those deposits, developing conceptual ground models in those terrains is extremely important, particularly in terms of looking at the reduction of risk and the reduction of uncertainty. And so hopefully I'll illustrate this with a few case studies. And as I said, I'll talk you through a little bit about what we did at the working party in terms of how we brought together some very disparate disciplines. We had fights, we had punch-ups, we had words we weren't allowed to use. And it was quite an interesting story about what happens when you start to develop a multidisciplinary report and then try and actually put it together into something that can be used by where we work in engineering geology in the ground industry. Now you may think, why hasn't this been done before? I mean, she started to look at the history of what had been done in terms of the Quaternary in terms of the UK, and we haven't really done anything. This is a lovely quote from a chap called Gilbert in 1890, was the USGS monograph number 1, and he said, when the work of the geologist is finished and his final comprehensive report written, the largest and most important chapter will be upon the latest and shortest of the geological periods. So even back in the 1890s, the Quaternary was recognised as being a significant period of geological time. Yet, it wasn't until 1991 that the engineering group really first addressed aspects of the Quaternary, and then our working party then started in 2017. And when we actually look at the sort of body of knowledge that we've put in our specific discipline of engineering geology, we've got very few key documents that we can actually refer to. A couple of serial reports, some ICE manuals, and this is what really prompted us to follow on from the last working party, which was on hot deserts, to try and start to look at all aspects of engineering in these most recent geological period, or perhaps that's not true now. The most recent geological period, I believe, is now the Anthropocene, and so if you like, the penultimate geological period in terms of what was the major climatic fluctuations during the Quaternary. And we started off on this risk journey back in 2011. We had a forum in this room. We had a one-day meeting where we invited various experts from across both the geological geotechnical, engineering geological, and more significantly, the geographical disciplines. This was really the first time that we reached out into the physical geographers and saw and asked what they were doing in terms of these particular terrains, and then started to try and distill some of that knowledge. And I'll show you some examples later of how important that was in this multidisciplinary approach in the development of this particular report. So what we set out to do is effectively have a look at a state-of-the-art review of the ground conditions associated with former Quaternary, Periglacial and Glacial environments. We focused very much on terms of the UK, and we didn't really want to start producing maps. We discovered very, very quickly when we delved into the Quaternary literature, there was a lot of disagreement about the extent of where ice sheets advanced over the British Isles, where they stood still, and where they retreated. We found there was actually warring geography departments across the country. We tiptoed into a little bit of a political environment. In engineering geology, we were used to dealing with facts. You know, you went out into the field, you described a borehole in terms of BS 5930, you had factual information, and then you produced an interpretation based on that factual information. We found ourselves tiptoeing into areas where that was not necessarily the case. Very academic discipline, where you could have ideas, where you could postulate models, and not necessarily have the responsibility that then went with that postulation of that model. Whereas ground engineering, we had to actually come up with a correct interpretation, because that's what the construction project depended upon. So we were wary about what we could do, what we couldn't do. And what we set out to do was to produce this essentially a modern-day reference book that started to inform the ground engineer of what they might expect in these particular terrains, delivered through the medium of a ground model, a conceptual ground model, how we might use ground models to describe what we might actually encounter. So we had this British Isles focus, and we wanted to understand about relic materials, relic landforms, but we dealt only with the cold parts of the Quaternary. We thought we were going to bite off more than we can chew if we went into the interglacials, the warmer climatic times, and so we really were dealing with relic cold environments. Cold and very cold and extremely cold environments is what we were trying to look at in terms of what we were doing in terms of the Quaternary. And so we started to develop an extensive glossary, and we started to develop this land system approach, how we could start to consider ground models that we could use in these particular environments. And what I'll talk you through is, the various stages that we looked at, the information we collected, and the significance of that in terms of engineering geology. So our key theme was the inherent complexity in glaciated and periglaciated terrains. We've all graduated from structural geology courses where the structural geologist tells you how wonderfully complicated the whole geological setting is. Yet, when we go into a glaciated terrain and a periglaciated terrain, this is not a complexity on hundreds of kilometers, on tens of kilometers. This is a complexity on the meter scale and even on the sub-centimeter scale, where we can start to see variability in the materials that we're actually starting to deal with. So we've got extremely important message to put across, that these are very, very complicated terrains. They vary both vertically and laterally over very, very short distances. And if we don't understand that variability, then we can start to run into problems in terms of the construction project. So we knew that engineers liked risk registers, and so we had a mind to start to develop our ground models with a risk register approach, how we can start to feed into that understanding, how we can start to delineate risk, how we can start to reduce the uncertainty if we're working in these particular terrains. We're also extremely wary that when you start to look through the literature and guidebooks and just the sort of general, if you like, geography textbooks, there was a whole variety of terminology out there. There was numerous terms used by numerous authors for the kinds of materials that we then dealt with on a day-to-day basis in engineering geology. And one of the key themes was really to set out how we could simplify that nomenclature, how we could reclassify glacial till, how we could reclassify glaciogenic and periglacial deposits, so that the practicing engineer can go out into the field and would be comfortable in their description and in their interpretation. We discovered when we started searching for some of these terms, the internet's a wonderful place. You can type anything into Google and up come thousands of images. Some of the terms that are out there, you could type them into Google and absolutely nothing would come up. They were terms that had just migrated through as throwaway one-liners that had entrenched themselves into the literature. So we set out to very clearly to come up with some definitions that could be used in engineering practice when undertaking ground investigations and site investigations, etc. And the other key theme that was often lost in the geotechnical world was the importance of ice, the importance particularly of segregated ice during periglacial conditions. What that meant in terms of the shear strength of materials, what that meant in terms of material fabric, what that meant in terms of geohazards that might be encountered in slope stability, for example. So we were able to start to understand about ice growth, and the impact of both on the fabric of the material, and then particularly in terms of pore water pressures, in terms of groundwater and moisture conditions within the soil. So we started to develop these themes underlying what we were trying to achieve in appreciating the variability and the performance in these particular terrains. So we had a multidisciplinary approach. We actually recruited from a wide variety of disciplines. We had our, if you like, our bulk standard engineering geologists. We then went into the Quaternary world, where we recruited some effectively Quaternary sedimentologists. We had geomorphologists, and we also had archaeologists as well. There was an element there where understanding sort of slightly more modern processes also gave us an insight into what we might interpret in terms of these Quaternary ground models. And we looked at all the information that was available, and we started to then cut through it to try and distill what do we want in terms of engineering geology, in terms of practicing in ground engineering, what are those key information sets that we need to draw out of that. So behind all this was the understanding of ground risk. We're going to go and work in construction. We don't want things to go wrong. We do not want to have unforeseen ground conditions. And yet here we were working in materials, working in landscapes that were both laterally and vertically variable. They had a great diversity of materials that were actually present. They had the soil variability, the rock modification, changed in strength, changed in permeability, changed in engineering behavior. We wanted to understand how we could classify that, how we could predict that through the medium of ground models to understand what we might encounter in those particular environments. We had a diversity of landforms, which were the legacy of ice sheets advancing and ice sheets retreating, of glacial conditions, a legacy of periglacial conditions. We needed to understand about reactivation. We needed to understand about their identification. How could we train ourselves as geomorphologists? Again, many pure geology degrees, geomorphology was not seen as a geological discipline. In engineering geology, we very much have pushed engineering geomorphology, reading the terrain as a key skill to understand what's underneath that particular, those conditions underneath that particular landscape. So we needed to understand about the diversity of landforms, how again we might classify them, how we might understand the potential engineering impact that those landforms had. And at the bottom line for this was we started to realize that if we were going to reduce the risk, reduce the uncertainty, we had to have education, we had to have field experience. At Portsmouth, we're seeing our geological fieldwork being condensed and condensed and condensed. Rather than expanding that field work out and looking at more and varied terrains, looking at quaternary terrains, the mantra of the best geologist is still the one who's seen the most rocks, who's still seen the most landscapes, who's still seen the most variability. Many of you have got varied sites, you're seeing that as part of your careers, but in terms of the undergraduate training, this is something that's being condensed, and we were trying to push back on that the field is still the place to learn, it's still to understand this variability in terms of what might be encountered. So let's have a look at a little bit of the background then, and what do we mean by the Quaternary? Why do we have these key themes? What gives rise to this variability? Quaternary, a period of major climatic change. We've seen ice sheet advance, we've seen ice sheet retreat. We've seen very, very cold periods, which are termed stadials. So the colder it is, the further south the ice will then travel. Even within a glacial stage, we can have an interstadial, we can have ice retreat. So this is a period of advancing and retreating ice sheets, of continual landscape modification, of continual deposition, reworking and redeposition of materials. Sea levels rising and falling, isostatic depression, isostatic recovery. We've got a very, very dynamic landscape that's being affected by these ice sheets travelling southwards as the climate then deteriorates. But it's not just in the Quaternary about cold conditions. We've also got to consider when we actually had warm conditions, and we had very warm conditions. The lions in Trafalgar Square are real. There were lions in Trafalgar Square. I mean, the Cromerian, there was hippopotamuses across the British Isles. We can find, Ipswichian, beg your pardon. In the Ipswichian, we've got many hippo remains across the British Isles. Now you say, that's just climatic fluctuation, but in geotechnics, that becomes significant because these are the materials we're encountering. They've had this post-deposition modification and weathering. We've got the climatic fluctuations to really understand what's happening to the fabric, what's happening to the strength of those materials. So our geology degrees tell us where all our rocks are in the British Isles. We know our stratigraphy from our Precambrian right up into the Jurassic and Cretaceous and the Tertiary. But when we actually look, where are our Quaternary deposits? Where are our Quaternary land systems? Everywhere. There's nowhere in Britain, there's nowhere in the entire globe where we can't dig a hole and we're coming up with some Quaternary influence. Even in London today, we're starting to more fully appreciate the influence of Quaternary conditions on that subsurface development in terms of the periglaciation, in terms of isostatic recovery, groundwater change, all happening in this Quaternary environment. So it's an extremely important period for ground engineering to fully appreciate that variability that's actually present within those conditions. We've had major ice advances, we've had major periods of glaciation. And these are some of the boundary lines that we've kind of had to battle with. These are almost chiseled out in granite in some of the Quaternary literature of where there's this solid line. The ice parked itself along the red line, the ice parked itself along the blue line. It didn't actually move. And we've had to actually deal with this in terms of understanding about variability, break down some of these preconceptions. We've got, as we'll see in a moment from a little animation, we've got a highly dynamic environment of an ice advance and ice retreat. Advance and retreat, continual reworking, continual deposition. We can also look at the areas which were periglaciated. We can look at the areas which were dominated by permafrost conditions. So to the south of the ice limit, we would have permafrost, and as the ice then started to retreat, we would have had glacial conditions as well as periglacial conditions. Two separate modification processes taking place in terms of that ground profile. And you can start to see from the maps that are appearing, we're starting to break it down into regions. If we've understood that climatic history during that past 2.6, 2.7 million years, we can start to predict the ground conditions. We can start to predict the variability. We can start to reduce the uncertainty in terms of what we might expect in those particular areas. So these paleogeographies, although physical lines are perhaps over-egging where the ice actually went, understanding the broad regions where they've experienced those different climatic conditions becomes extremely important in the development of these ground models in terms of potential prediction. We've got other processes then taking place as well. This is extremely important for some of you maybe working with some of the next generation of nuclear power stations, looking at Sizewell, looking at Wilfer, looking at Hinkley Point. We've had major levels of sea level fluctuation. We've had fluvial processes. We've then had temperate weathering that's taken place as well as the weathering in the glacial and periglacial environments. We've got a very dynamic landscape over this very, very short period of geological time that we need to fully understand if we're going to start to develop these predictive models to understand this lateral and horizontal complexity, the legacy of these conditions, the legacy of these climatic conditions left within the terrain that we're potentially engineering in. So if we actually look at perhaps some of our big projects that are going on at the moment and seeing why this then becomes significant. And we've got HS2 coming out of London. When we actually look at that map of those paleo environments, HS2 is going to be traversing across all of those different terrains, both periglaciated and glaciated terrains. And if you want to understand about that complexity, and we've traditionally talked about there being 3 ice ages. If it works, this should work. This is a little animation, if you look on the bottom left there, produced by the University of Aberystwyth, part of the BritIce project, in collaboration with Sheffield University. They've actually done traverses across Britain, they've dated the geological Quaternary deposits, and they've reconstructed it into an animation of ice activity, ice advance, ice velocity, and ice thickness. And let's see if it works. And this is an animation of effectively the period from about 37,000 years ago to 10,000 years ago, looking at ice growth and ice retreat. So remember these lines on the map, these red and blue lines of the ice parked itself there, didn't really travel any further. This is what's happening in terms of the animation. We're seeing major ice sheet growth, the Scottish Highlands, the Lake District, the Cheviot Hills, ice retreat, then an explosion of ice right down into effectively North London, the Bristol Channel, then another retreat. So this is these climatic fluctuations, these Milankovitch cycles, these oscillations. Now, geotechnically, every time you see it explode and then retreat, that's the ground profile being modified. That's a new set of deposits being formed, a new groundwater regime in that particular environment. So we've got this extremely dynamic terrain that's then being generated by these climatic fluctuations. So it isn't a case of one move forward, one retreat back. We've got a very varied, very complicated legacy because of that ice sheet growth and that ice sheet decay. Has it stopped? This is a most fantastic photograph. I think this is one of the finest photographs that really defines the Quaternary. This was acquired by a couple of the co-authors, David Evans being one from Durham University, working on the Working Party report of a glacial interface in Iceland. And this is effectively, if you want to sort of look at it another way, this is HS2 coming out of London. HS2 comes out of North London and then crisscrosses that boundary. It crisscrosses a terrain where sediments have been glaciotectonized. They've been shunted up in a series of thrusts and ramps and folds. We then have a large area of a glacial lake. We have icebergs rafting material across, depositing it in very fine-grained sediments. We then have the actual ice margin itself. We have material being deposited underneath the ice, material being deposited from on top of the ice. The ice sheet then retreats, and that's the terrain that we've then got to interpret with boreholes. If you were to do a borehole survey across that interface, how many holes would you need to really fully characterize that variability that you could find? It would be impossible. You would have to absolutely, almost roll back geological time to actually see what had taken place. And this is why the ground model then becomes so important. We need to develop ground models from these contemporary terrains and then start to understand what that means in terms of the relic ground conditions, what's left behind in terms of that ground profile. So we need to understand our legacy, the engineering risks posed by these quaternary conditions. And we've got lots of case studies. We've got some very classic case studies in engineering geology. This is the M6 construction up in Walton's Wood in Staffordshire. And as part of that construction, there was a major embankment failure. It was then the post-failure investigation found all sorts of shear surfaces, all sorts of variability in the glaciogenic and periglacial conditions that are actually present in that ground profile. And perhaps this is back in the mid-1960s. Someone correct me if I'm wrong, it's about 1965. For the first time, there was a failure that was directly linked to those underlying Quaternary Legacy conditions. So how do we then go about dealing with that engineering risk? What do we need to do in terms of the development of our particular ground models? We can start by taking a terrain classification approach. We can start at the macro. We can start looking at the extremely big picture, back to the potential areas that have been glaciated, areas that have been periglaciated. And then we can start to subdivide that from provinces down to domains into specific land systems, and then start to develop our engineering ground models. We can start to actually build through the building blocks that we have to appreciate what's the legacy that we might find in these particular environments. So we can look at different models in terms of ground models. We can look at land systems, areas that have common terrain attributes. And what the physical geographers brought to us, they said, well, we can also look at process form models. We can start to look at the genetic interrelationships of the landforms and the sediments. And if you're getting a certain sediment profile, what else might you expect to find in that particular environment? We've got a different way of looking about how we then start to develop a ground model, how we think as geologists, how we can put our three-dimensional knowledge and our four-dimensional knowledge into a conceptual model as a predictive tool to help us understand that complexity of that marginal environment, as we saw from the ice front from Iceland. So we've got these different models that we can then start to use. We're perhaps used to using analytical models, and we all like putting numbers into slope stability equations, finite element, finite difference models. We've got our real data, our observational data when we go out in the field. But conceptually, we want to start by illustrating the key features of the geological situation and both active and relic processes we can find in a particular environment. This is what we're trying to focus in on the Working Party, how we then support the development of those conceptual ground models, how we can start to have this predictive tool about what we might encounter in those particular terrains. So how do we go about informing the ground model? Well, our basic geological training doesn't go away. The great Charles Lyell quotation of "the present is the key to the past." And again, this was very useful from our geography colleagues. You know, they were going to Siberia, they were going to northern Canada, they were going to Iceland, they were looking at modern glacial environments. And we were able to interpret those modern environments to understand what that meant to the relic terrains that we were encountering in terms of ground engineering, in terms of engineering geology. We started to appreciate that we needed to understand that Quaternary history, you know, the climatic fluctuations, you know, whether we had cold, very cold, or more temperate environments. What did that mean in terms of the genesis of the glacial and periglacial materials? And then we came along with our geotechnical spin, with our geohazard spin, to understand what was the significance for the ground model. So we had this flow chart where we could start to interlink that basic paleogeographies, the geological histories, then start to understand about the sedimentology, the glacial sedimentology, and then the geotechnics, and then the geohazards, how we had that throughput of linking all that knowledge together, which again was at the heart of the working party, where this was a multidisciplinary approach. You know, these were areas that geologists had traditionally not looked at. They would never have a clue about the Quaternary history. The glacial materials were just seen as the horrible stuff on the top that we didn't really bother with till we got to the proper things underneath, which were the rocks. And this was a kind of major advance for us to start to have that link that was actually present. So what do we then need to do then? What do we mean by the engineering and geohazard significance? We need to be able to understand these materials, understand their behaviour, understand what geohazards are present if we're going to start to reduce the uncertainty in our construction project, if we're going to start to reduce the risk. We need to understand the basic environment of deposition. We're good at that as geologists. We've done environmental depositional environments in our sedimentology. Have we got glacial materials? Have we got fluvial glacial materials? Is it glacial marine? Is it glaciolacustrine? You know, that fundamental depositional model helps us then develop the understanding of the variability in the strength, the variability in the permeability, what potential geohazards are actually present. And what we also then need to bring to this is the appreciation, as I said earlier, about the significance of the scale of the lateral and vertical variability. So we start to build on that history, build on that genesis, and then start to feed that into our ground model to reduce that risk, to reduce that uncertainty. So what do we need to do that? Well, we need a catalogue. We need a catalogue of effectively the building blocks that make up that terrain, the building blocks that make up that ground model. And the building blocks are the sediments. The building blocks are the structures, the landforms that are present. And we saw that we can have macro structures, and something that came to the working party quite late was we started to discover we had microstructures as well. And we all remember with fondness going on doing a geology degree, looking at thousands of thin sections of bits of granite, and we thought we'd left those behind perhaps when we graduated. Some of you may not have left those behind, but in terms of engineering geology. But we started to see that we can start to look at thin sections now of some of these glacial sediments, telling us about the deposits that are present, telling us about the stress history that's present. So we needed this complete catalogue from the macro to the micro that helps us inform the ground model, that helps us understand what's present. We had to develop our land system into effectively its subunits. We started to look at the periglaciated terrains and the glaciated terrains and think about how we can break them down further. What land systems did we have present? Well, we had lowland land systems, we had upland land systems, we had soft rock, we had hard rock, we had slopes, we had valley floors. Effectively taking some scissors to the landscape and chopping it up into its component parts and starting to understand what are the building blocks that make up those individual components. So we can start with our desk study, knowing we're going into a certain area, knowing that Quaternary history, knowing the kinds of slopes, the kinds of rocks that are present, and then start to build up that understanding, start to build up that predictive model of what's actually present in those terrains. So we did this for the periglacial terrain, and with the glaciologists, we also did it in terms of the glacial land system. We looked at modern glacial settings, understanding where we had ice sheets, where we had valley glacier systems, whether we had outwash systems, what happened when the ice met the sea, particularly important for many of our offshore oil fields, wind farms, and connector cable projects. What was the interaction that took place when the ice actually went into marine conditions? This subset of ground models fed through with the different component parts, fed through with the sediments that are actually present that make up that particular land system. We also started to look at the individual deposits. We started to, as I said earlier, started to go through the different environments and what materials might we expect to find with a specific target that they could be recognised in the field, they could be recognised in a borehole. We wanted to come up with definitions that were transportable into a site investigation and that these materials were actually recognisable. So we had to throw a lot of terms away. There was a lot of dialogue about what terms we could utilise. We actually had quite a considerable argument in the working party. There's a term that is much loved in physical geography called a diamict and a diamicton. And in terms of engineering geology, it's a term that's hated because it doesn't mean anything. And there was some serious discussions and almost shouting about where we got, where we could actually get to this. And my graduates in the audience will know there's one term we don't use, which is the BC term that migrated throughout, the boulder clay term, and how you actually remove this from the literature. I have never seen a boulder clay. And I challenged everyone on the working party, and one of the working party had seen a boulder clay in Canada, but we'd seen lots of clay boulders, but never a boulder clay. And we got this legacy term. It transpired that it was an American term. It wasn't even a British term that had been entrenched in our maps with the Geological Survey that we then had to remove. So we had a terminology that we needed to put in place that accurately reflected the sediments that we're actually starting to log and starting to encounter in the field. We also then started to look at some of the structures that are present. We started to appreciate that if we're going into contaminated land, if we're going into foundation design, structures and fabrics become important in terms of stability. They become important in terms of potential pathways. Gain this lateral and vertical variability. And so this project was becoming a fast breeder project. Every time we had a discussion, we realized there was more and more building blocks that we needed in the document that supported the developing ground model. So it started to expand really quite considerably. The chapter that this all feeds into is in excess of 300 pages by now, because there's effectively an atlas. I'll show you some of the slides in a moment of the atlas of the materials and the structures that we then started to categorize and define that form the building blocks for the ground model. And we went back, as I said a moment ago, we went back to the thin sections. We started to realize that the microstructures within our deposits told us a lot about the stress history. If you link through to structural engineers, they want to know about the stress conditions, they want to know about the stiffness of the ground, they want to know about the ground performance. And we could start to look at thin sections. They weren't actually thin sections, they were plates about this big. They were quite significant and very skilled in terms of their preparation as a thin section of the materials. But you could start to see fabric within the soil. You could start to see alignment. You could start to see shearing that had then taken place. And again, with a view to potential reactivation. This was an extremely interesting, this was the last bolt-on in terms of the whole project that we started to realize. There's this new discipline. Professor Emrys Phillips from the BGS really brought a whole new way of looking at soils and in terms of geotechnics, understanding the soil and how that might potentially behave. So we've gone from the macro, we've gone from the large, right down to the thin section, right down to the micro level. And we produced a catalogue too of the different landforms that were present. What landforms might we expect to encounter in these particular terrains? And landform recognition, again, because of the lack of fieldwork that we do, landform recognition became extremely important. If you can go out and recognize you've got a potential geological hazard, a geohazard in that terrain, what is the landform you're looking at, we can start to understand the impact that means in terms of the risk to the engineering project. And then lastly, what we then did with this catalogue, we then used that expertise as part of the working party to understand its true engineering significance. We started to appreciate this variability. We started to appreciate the different soils that are present, the different structures, the different landforms. What did that mean in terms of the ground engineering? What did that mean in terms of the construction project? So we interrelated the geomorphology, the geography, and the geotechnics to start to define the engineering significance. So work that was done very early on by John Hutchinson, late John Hutchinson of Imperial College, when he started to build up these diagrams. If you're going to work in this terrain, what can you expect and what does it mean? How can it affect your particular project? So we started to categorize our landforms, our deposits, with a significance, how they might affect a particular ground engineering project. And the key part of the sediments was that we developed this new nomenclature. We realized that in engineering, geology and ground engineering, we were used to using British standards to describe rocks and soils. There was a set rock names and set soil names. So we started to actually look at what we might utilize for a series of labels for particular deposits. And we condensed the glacial deposits down to 4. So rather than what was, we started with about 25 different labels for glaciogenic deposits, we've now got 4 that we define. 1 very, very rare, and 3 really quite common in terms of what we might find in a terrain. So we've given the engineering geologist a tool to actually be able to classify these and understand their genesis and understand their significance. And again, similarly, we did this with periglacial deposits. And part of the working party was to produce a poster, and I'll pass the link on so that can go on to the Home Counties North webpage. We've got a nice A0 poster, which again has this classification, has this nomenclature with examples. So we're trying to hopefully produce a valuable tool for people working in the field, that they have these labels that they can attach and understand what that means in terms of the significance of the material, in terms of the material's variability. So what we did was we produced effectively an atlas. If you remember back to your undergraduate days, you had the Atlas of Rock-Forming Minerals, Atlas of Igneous Rocks. Well, we produced effectively a visual atlas of the sediments, and we looked at their terms, their diagnostic characteristics, putting across that environment, that depositional environment or formation, what structures you might expect to find, as well as their engineering significance. And we fully illustrated this throughout with examples from the field, with contemporary examples from modern analogues, as well as relic examples of what we might find in a ground investigation. And we've added in their sedimentological description, but we were very fortunate to have Dave Norbury working with us, and he went through all of these photographs and put an example engineering classification that you might utilize with these particular deposits. So we've got these structured tables that tell us about the sediments. We did the same thing with the macro structures, looking at their significance. We also added in case studies, I should say, as well. And for each of the structures, we put in an engineering case study that was an example, references of where these have been encountered before. Here's our thin sections. This was the work from Emrys Phillips, starting to show us in plain light, plain polarized light and cross polars, how we can start to even look at the thin sections to interpret these deposits with a view to understanding their particular engineering significance. So we've got a whole atlas in the Working Party report demonstrating examples of the deposits and structures we might find. And then lastly, we went through the landforms. We looked at the modern landforms, trying to give an example of what it might look like as a contemporary form, and then what a relic landform will actually look like. You know, it's sometimes very hard to put across in a photograph. What we wanted to really come out of the if you like, the legacy of the Working Party was to try and develop field training courses. Many of you have been on Jackie Skipper's course, or you've been on Rory Mortimer's course. You know, you looked at Dave Norbury's soil logging course. How many of you have been out in the field doing an engineering geomorphological training course or looking at quaternary environments? This is something that's really missing from the modern day, if you like, geoscience training portfolio, how you can then kind of further develop those skills. So this was something was a recommendation really from the Working Party, that we needed to take people out and actually see some of these particular landforms. So again, highlighting their engineering significance. And as we saw, when we first started this, we were thinking, well, some of these things you're never going to encounter. And then suddenly someone got a job in Azerbaijan, someone got a job in Georgia, someone got a job in Sakhalin Island, you know, where there were these environments where suddenly they were having to understand. They weren't necessarily UK-based, but they were still a UK office-based, and then starting to actually interpret these complex glaciated and periglaciated environments. And at the core of this was our geo team. As I said at the beginning, you know, we got together all this quaternary knowledge, all this field experience, and that's really what the Working Party was trying to distill. And there's a real plug here for those of you working in ground engineering, that there's quite a large untapped resource. You know, we've got several very, very good MSCs across the country, Durham and Roy and Holloway, looking at quaternary deposits, effectively very structured quaternary sedimentologists. They're trained in soils description, they have that good background knowledge, but they haven't made the leap across into ground engineering. And many of you trying to recruit from the geotechnical field, there's a very good physical geography resource there for looking at these particular environments. You know, are used to these terrains, perhaps not used to the rigor of the construction industry, but have the necessary knowledge and field experience to really bring something to your construction projects. So we distilled all this into the ground model. So we had our building blocks, and then we decided that we actually needed to visualize this by the generation of a whole variety of what are effectively conceptual ground models. So perhaps you're used to sort of seeing these quite frequently now, how you've got a particular terrain, and there's the sort of landforms, there's the sediments, there's the variability in these particular terrains. Here's one for effectively a dry chalk valley system. And I've actually tested this out. It was a bit like an I Spy exercise. We took our students to Freshwater Bay on the Isle of Wight, and it wasn't quite 10 points for every landform or deposit that you find, but there was our predictive model. We went out into the field, and we were able to actually start to identify them in the fields. This was our sort of, if you like, the pre-knowledge that was required when going out into a particular site. We could take our conceptual model, our 3D block, and then start to pick out the various landforms, pick out the deposits, because we had this forewarning of what we might encounter. So we don't have to have the factual information, we can have the conceptual information that we can then start to ground truth when we go out into the field. So there's a whole variety of these we produced for these different terrains. This is Bath, rhyolitic limestone cap rock on top of the Fuller's Earth, where we've got valley bulging, where we've got cambering, where we've got gulls. Again, an expectation of what you might find in that particular terrain, given that Quaternary history, given those lithologies that are present, and what is the legacy that's actually present left behind. So we distilled all this, just finishing off really into our engineering geology special publication, just to tell you a little bit about the kind of nitty-gritty of it. That was really the sort of, if you like, the ethos behind what we were trying to develop. It came out October last year, and part of our talks from the working parties going around the country sort of trying to explain, you know, what we set out to achieve. There's our working party, and we had very esteemed engineering geologists from both academia, Geological Survey and industry, but we also linked through to those Quaternary specialists. We had Julian Merton from down at University of Sussex, who's perhaps one of the most eminent periglacial specialists, and we had Sven Lucas from University of London, and David Evans from University of Durham, bringing that Quaternary expertise that was present. And that's why the dialogues then got interesting. I'll show you a case study in a moment where that really came to fruition, where the left hand finally spoke to the right hand, and we started to realize that we really kind of had both disciplines could offer something. So this, back to this Dennis Brunsden geo team, that was very important about the working party, that it had this multidisciplinary disciplinary approach. The book is structured, effectively, as I've been talking through. It's structured in terms of the background to the Quaternary, how we can then start to inform engineering geologists about those big climatic fluctuations, perhaps demythifying some of the if you like, the old knowledge that's out there, trying to actually put across. We don't just have an ice age, we've got these major fluctuations. We established the geomorphological framework, the building blocks for the ground model, and then we had the specialist Quaternary geographers bringing us periglacial conditions, what was significant in the periglacial conditions, as well as the glacial conditions. Then back to the engineering geologists for their geotechnical properties and their geotechnical performance. We also thought it was very important in this kind of new discipline that perhaps wasn't natural to graduate geologists, graduate geoscientists, how to actually use the book, how do you actually use it as a reference tool. So we've actually added in a guide to actually how you assimilate, how you build your model, how you actually integrate that data into a conceptual model before you actually start to go out and working in the field. We felt that was very important to not just produce a massive text, a massive tome, but there was actually some information as to how to use that information, how to guide you through it. And the feedback we've had so far, this has perhaps been one of the most useful pages really, and actually sort of saying how you get access to that information, how you then go and develop that ground model. We also linked through to our Quaternary colleagues further, and we had a very comprehensive reference list. It was very important that we demonstrated the contemporary glacial and periglacial research, started to link through the stuff that's happening in the North Sea, the stuff that's happening in terms of some of the major research investigations into active glacial, active periglacial areas. And we also wanted to bring to the attention of the geoscience community what the Quaternary Research Association was doing. There's a magnificent set of field guides covering all of the British Isles, and they're now available online as PDF documents, as a field guide. So you can actually go out before you start a project and go to these sites and start to appreciate this variability, part of the kind of, if you like, the continuing education that's then present. We've got the Glacial Landsystem divided up into its component parts. We've done the same thing with the Periglacial Landsystem. We start this, if you like, the key chapters in terms of understanding these particular terrains, from Julian Merton and from David Evans, building up the subdivisions, understanding their interconnectivity. We went through the materials, and the document really starts to describe what we mean by these 4 different fundamental materials. You may notice from the materials at the bottom, there is no boulder clay. There is no lodgement till. We all arrived at this process thinking we'd matured out of boulder clay, calling everything lodgement till. And then David Evans said he'd only seen lodgement till once. This is the guy that's wrote a book on tills this thick. He'd never ever seen lodgement till. And there's our entire industry calling everything a lodgement till. Yet he'd never ever seen one. He thought he'd seen one once on Skye. And so we were breaking down some major misconceptions from the contemporary research in terms of what we have in terms of the materials. So we've got materials that's dragged along at the base of the ice, material that's shunted by the ice, material that effectively gets released from the ice by melt-out. So we've got different properties, but just 4 materials in terms of those fundamental glacial processes. The BGS came along and then started to help us look at some of the geotechnics of these materials. So in the document, we started looking at their geotechnical variability. So again, as a predictive tool, if you've got a former glacial lake, you can expect to find these glacial extreme deposits. How do they vary geotechnically? What could you encounter? How may that help you when you test for them? What are you going to look for when you start to ram a shell and auger rig through them and destroy the fabric of the material? What might have been there before you buggered it up with your ground investigation? Simply because you didn't find it doesn't mean that it's not in that particular relic terrain. And that, again, was a very important aspect of the ground model development. We started to bring through the geological hazards. What's the variability in terms of potential large-scale or medium-scale geological hazards? Have we got more regional geohazards in terms of sea level rise and sea level fall? Starting to look through, what's the expectation? And we started, I'm not going to go through that in detail, but what were the engineering challenges of this spatial variability? That was the sort of starting to get into the concluding chapters. We've got all these building blocks. We've put it into a conceptual model. What does that mean in terms of our construction? What are the challenges we need to understand about permeability, about particle size distribution, about suddenly having very large particles, boulders in finer grained sediments? Where have we got a whole series of buried channels and tunnel valleys? That's what the graphic is showing you there around Doncaster. Who'd have thought that around Doncaster, the M1 had such a complexity of terrain with this entire paleo valley system that was present? Maybe completely miss it on a borehole investigation. If HS2 does its boreholes at 3 miles apart, you're going to miss these kinds of features. We're now at the 1 metre, the 10 metre, the 25 metre scale. If we don't have our conceptual model, we won't understand the engineering challenges in that particular ground profile. So we put across this key message of variability, complexity, and uncertainty, and then how you then build that into the design and the construction process, how you reduce that uncertainty to get a better understanding of that variability within those particular ground conditions. And the last part of the book, just take you through the last part of the talk, was we scoured for a whole series of case studies. So we've got a variety of case studies, both in glacial conditions and in periglacial conditions. And I'll focus on this one in particular, because this really kind of summarized how we, if you like, matured and advanced in terms of engineering geology of what we did in the whole process. We had 2 field trips while we were doing the working party. First of all, we went up to Scarborough, and we saw this variety in tills that we'd never really seen before, and dispelled the myth of boulder clay, dispelled the myth of lodgement till. And then we went down to Sevenoaks. The Sevenoaks bypass is really a kind of seminal case study in engineering geology. It's one of our kind of holy grail case studies where perhaps for the first time we discovered solifluction lobes, and reactivation of shear surfaces. So this was a site which was characterized by the process of solifluction, the legacy of solifluction. And so we took our glacial specialist and we took our periglacial specialist from their quaternary environment, and we said, come and look at our magnificent solifluction site. And they said, that's not solifluction. They're active layer detachment slides. They're full of shear surfaces. Why would you have shear surfaces in something that's moved as a liquid, than something that's moved as a supersaturated mass? So 50 years of our orthodoxy of Sevenoaks being a classic site of solifluction was then rethought in terms of modern analogues, in terms of active layers, the thawing layer in permafrost, detaching and then starting to shear. So we really had challenged what we thought, what we thought we understood in terms of that periglacial ground model. By talking to those other disciplines, there was suddenly a very different reinterpretation, a different understanding of the process of flow, which is solifluction, and the process of sliding, where we had these the active layer, the thawing layer in the permafrost, detaching and then moving down slope on a shearing surface. And hence that's all of our relic shear surfaces that are present. So we felt it was very important to take these different case studies then to illustrate these key issues. We put some classic ones in there, the quick clay landslides in Riise in Norway. It's a very interesting lecture in its own right there about how you can have isostatic recovery and you get a modification of the soil profile. You remove the salt dissolved in the pore waters, you replace it with fresh water, you get a reduction in strength, you get a very different kinds of engineering behaviour, a legacy from that Quaternary history, a legacy from marine deposits being silts being deposited in marine conditions, being lifted above sea level by isostatic recovery, that saline pore waters being flushed out and getting a very problematic soil, a very problematic geological hazard. So we started to explain this in terms of that history and what does that mean in terms of the geotechnical legacy. David Norbury was very kind to share his early knowledge on the Carsington Embankment Dam failure, the very famous yellow clay. Again, that periglacial legacy, completely overlooked and not seen of any significance at the time. So it took a major failure for us to really start to understand these. So we put these in as examples as to why these particular conditions are important. I put a case study from down in the south of France in. This was the autoroute from Grenoble to Sisteron, which was crossing this glacial lake environment, and where that depositional model became extremely important. The variability of shallow water, of deep water, of near ice front, ice advancing, ice retreating, giving a whole variety of different geotechnical materials which were highly significant in the design of the embankments. The material was very prone to liquefaction failure. If it was disturbed, you would completely lose the strength of this material. There's very large landslides that are occurring there. So the fundamental paleogeography linked through to the depositional environment, linked through to the geotechnical invariability was part of that developed ground model. So integrating all of those different disciplines, feeding through into the construction project. And this was a nice example from one of our former students at Portsmouth. He was happy to have gone on a nice Norfolk field course where he saw some of the great glaciotectonic structures, so very large chalk rafts that had been stacked against each other. He then found himself working offshore on a ground investigation for a pile design for a wind turbine. And the drilling crew hit chalk, and they decided, well, we've hit chalk, we've hit bedrock, that's enough, we can all go home now. And because he had his conceptual ground model, because he had the field experience of seeing the rafts, he decided, no, we will drill further. And true enough, they drilled right through the bottom of the chalk into the underlying glaciogenic deposits because it wasn't in situ. It was a huge 100-metre stack of chalk that had been ramped on top of each other. So the drilling crew were quite happy to stop in bedrock, but the ground model, the conceptual ground model, with all this history, with all this landforms and deposits, said no, drill further to prove the depth of the chalk. And luckily he did, otherwise there might be a very jaunty angled wind turbine now just off the coast of Norfolk. Professor Jim Griffiths down at Plymouth was very integral in some of the geomorphological works and geomorphological mapping down at the Channel Tunnel portal. And we've got a nice section here in looking again about how we can acquire the data sets, the geomorphological data sets to inform that ground model. And there's, if you ever get a chance to go and see some of the talks on the whole portal there's a very, very large landslide, again with a very interesting periglacial history that needed to be understood and overcome for the integrity of the tunnel as it entered at that portal site at Cheriton. So again, we're trying to exemplify these significant ground conditions with, if you like, some of these seminal case histories. We were chatting over tea before we started about some of the drift-filled hollows in London. These are, again, starting even now becoming, we're starting to understand their significance. I don't know if any of you saw last week that lovely image of the interferograms, the INSAR data that was acquired and picking up the settlement from the Crossrail tunnels going across London. We've got lots of interesting work now being done in Imperial College with Richard Gale, Philippa Mason, started off by Mike de Freitas, starting to look at the underlying faulted fabric as a quaternary model in London, starting to understand the significance to the river network, starting to understand the significance for our drift-filled hollows. And so we put in examples here of now we've got this very still unknown in terms of its origins about some of our quaternary structures. So we're encountering these on our ground investigation and construction projects on an extremely frequent basis in London. The American Embassy, that was some of the interesting delays with the American Embassy down in Battersea, had to encounter some of these. The Olympic Velodrome out in East London was sat on top of one of these particular quaternary features. And so we've got a significant geological hazard in a quaternary environment that we still really don't understand in terms of its genesis. And so our ground model helps us, understand that these could be predicted and starts to characterize what variability we might find within them. And lastly, we went offshore. We started to look at the, if you like, the flooding the English Channel land system as well. When we had the work on the original Channel Tunnel, and we had this very complicated tunnel valley system that was actually offshore. So again, we can't go and see that. Our boreholes won't necessarily pick that up. The bathymetric surveys at the time were good resolution, but not the kind of quality of resolution that we had today. But it is that, again, that ground model that started to predict what we might expect to find in terms of this paleo valley system, these great fosses, the Fosse Dangoard, that came really quite close to the Channel Tunnel. So we've got some offshore examples that are in there as well to sort of exemplify this variability, exemplify this complexity that's actually present. So the key conclusions really are that we've got inherent complexity. The quaternary environment is extremely variable. We need to understand about its climatic history. We need to understand about the deposits that are left behind and how those deposits have been continually been modified by reworking, modified by ice. And that's really the kind of essence of what we were trying to put across in this book. So it's a bargain. It's £60, thanks to all the sponsorship. We're very grateful to some of the major construction companies, consulting companies that helped us. It's just short of 1,000 pages thick, but as I say, most of that is this catalogue here that kind of helps support the development of the conceptual ground models in these relic glacial and periglacial environments. So thank you very much. Thank you. Thank you. Yeah, please. Yeah, is there are any?
Anyone would like to ask a question?
You get your own back now.
Tim over Atkins. I'm also one of Dave's former students as well. The image you've got on the cover, am I right in saying that's a drop stone, or is that something completely different?
That was a newspaper cutting from Washington State, a place called Everett in Washington, where this was. We found this in the Daily Mail, saying how there was unexpected ground conditions that appeared, and it kind of exemplified, what was meant by the geological hazard you might expect to find in glacial conditions. It is a very large drop stone into some glacial lacustrine deposits, surrounded by some tills. Everything in that hole varies on, the half a metre scale. And they were about to put down a piled construction there, and there was this great massive lump of rock there. So it really kind of exemplified, what we were trying to achieve by demonstrating lateral and vertical variability. I'm not sure we've acknowledged the photographer. I'm not sure he quite knows that it's actually on the book yet. So you might get a nice surprise one day. So he's acknowledged in it. So Daily Mail came in useful for something. So.
Given the variability of the glacial soils that you've described, is there any point in the geotechnical engineer using their pointy and blunt sticks to obtain numbers?
Well, that's again is a kind of key message. No, not really, because it is the variability. You have endpoints. In terms of you wanted to develop the risk model, you've got to take into account that full variability. You can't plump for one value, because the values will change from a minimum value to a maximum value, and they may not be normally distributed. And that's the kind of message across. It is this complexity. And we tend to sometimes use computer models, don't we, where we just put one number in, press a button, and it comes up with a wonderful graphic, and then off we go. Yet, as we're starting to see from some of the site work, that it is not like that in these terrains. And there's a lovely example across the road here. One of the talks that's been here previously, there's a basement development across in St James's where they did 6 boreholes, 5 of them were in London clay, and then suddenly one of them was in the Lambeth group. And then they started to dig some trenches, and they had some Thames gravels with a reverse fault going through the Thames gravels. Because it wasn't benign, it was that level of variability. So, 2 boreholes, everyone had gone away happy, designed it based on this basement based on London clay, yet you had this tremendous variability because there's these complex changes in this Quaternary time period. So it isn't this kind of, gardening, top veneer, nothing's happening, a lot is going on. A lot is going on sedimentologically, geotechnically, as well as structurally as well.
I remember...
You just need the microphone because it won't come out on the tape.
I remember at university, I did geography as a subsidiary subject, and they used to talk about re-excavation of existing valleys by the, when they've been filled in by boulder clay or till, and then they'd be re-excavated. How true is that? And wouldn't the simplest solution to drainage patterns on glaciated areas be simply imposed by the form and shape of water flowing in the ice?
I think it goes back to that the simulation that Aberystwyth and Sheffield produced. That every time that ice advances, it's reworking those ground conditions, it's re-eroding, it's redepositing.
Yeah, well, I'm talking about the actual drainage pattern imposed by the ice.
And again, every time there is a drainage pattern, the ice then retreats, you have an imposed drainage pattern, it advances again, and then that drainage pattern gets then modified. You've got considerable amounts of water in that system when the ice starts to melt. You've got very, very high energy, high volumes, high erosion that's then taking place. The ice then starts to advance again. You're getting sediment infill into that system. So it is a constant reworking. The pattern is continually changing. And the penultimate slide I showed you around Doncaster was really trying to, that's that sort of legacy of that Paleo Valley system, of that river network that's been imposed by the ice. And understanding, you may have a current day river network, but you've got all sorts of other imprints that lurk behind that from those previous ice advances, from those previous ice retreats. And there's some very big river systems that no longer have rivers in them. The Bytham River, for example, there's a very large river network that is not a river anymore. It's just a series of infilled valleys. That was a previous glaciation river fluvial network.
Yeah, hi Dave. Stuart Wagstaff. You probably wouldn't remember me anyway, but your first year was my last year at Portsmouth. I just wanted to know if the book covers sort of cryotubation and solid fluxion in sort of detail and how to recognise the soils, because you mentioned solid fluxion, but I sort of see cryotubation quite a lot occurring in.
This was a key component that Julian Merton really brought to his chapter, really understanding those freezing and thawing processes, the significance of ground ice, of segregated ice, what that meant in terms of the disruption to the fabric. And so all those issues that are kind of looked at about, and trying to differentiate between not having this kind of blanket term. If you have a lithology, that lithology has a pore space, it has effectively a class structure. What happens when ice starts to grow into that particular structure? What's the legacy of that? And that's a kind of key part of Julian's section, really, and sort of bringing, if you like, that cryological research into the legacy in terms of in the geotechnics. And again, we started, Julian sort of started to demonstrate this. We're looking at some of the experiments they're doing in Caen. So over the channel in France, they've got a big cryo lab over there, and starting to look at when the ground starts to freeze, the sort of the movement of water and the growth of ice through that freezing. And it started to effectively start to develop a line. Now, we were starting to recognize that line as a shear surface. So we started to think, well, that's actually a shear surface that's growing there by some of these cryotubation processes. So that was a nice integration of these. We perhaps would not have gone to the glaciologists. We would not have gone to the cryologists, the cryo specialists, to start to see. And Julian really brought that quite nicely into his chapter of looking at, the importance of ground ice, the importance of ice segregation, in terms of the legacy of that as a material. So that's a key aspect of his chapter. I should say that all the chapters, you don't have to buy the whole book, all the chapters are individually downloadable as well. So if you're interested in kind of that, you can actually download it piecemeal as well.
Hi, David. Ian Longworth, of course. Wind-blown silts. I don't think you mentioned them. I seem to remember going to the Ramsgate area with Hutch and looking at material which he said was effectively loess. How common are such materials in the UK?
That again was interesting. We went to the type locality of the loess down in Pegwell Bay. And again, that started back to the cryotubation. The loess in Pegwell Bay has these significant horizontal fissures, that would normally, if you kind of go in the old parlance, would have been sort of part of what you might have thought was over-consolidation. And then that was the discussion that started, with the periglacial specialists as the sort of the aspects of the imprint that freezing and thawing would have. And so we looked at loess as a material. We started to understand about the difference between loess and brick earth, as a significant periglacial deposit. So again, part of that key chapter was to break down the wind-blown sands, loess as a primary material, brick earth as perhaps a reworked loess, and what have you. So that's what we tried to actually sort of differentiate. What are the materials that you would expect to find in these environments, and then their significance. So yes, it's still thought of as a primary loess down in Pegwell Bay. And that, of course, was significant for high-speed 1 channel tunnel rail link, and then starting to potentially recognise that elsewhere as an infill. So.
Sorry, just one more. Nowhere in the talk tonight did you mention tunnel valleys.
That was the Doncaster slide, yeah. So the Paleo valleys and Doncaster, yeah. So tunnel valleys are in there.
Oh, yes.
Yeah.
And associated subjugated, localized depressions in the bedrock surface.
Yeah, that's all. That again, was the kind of the key message, that you had this highly variable terrain that then had this blanket of infill over. And what was the infill? What was the geotechnical variability? And again, if you're getting differential settlement, you get differential permeability. You're getting differential pathways if you're looking at contaminant models, for example. And that was a kind of key message, that you didn't have uniformity in the terrain at all. You had this legacy of valley systems, of tunnel valleys, of infill, of hollows, depending on where you were, linking through again to the bedrock, that link through, that if you had a lithology, how did that lithology respond to those climatic conditions? How did it respond to being glaciated? How did it respond to being periglaciated?
Now, some geographers tend to poo-poo the idea of tunnel valleys, and they create all sorts of theories of tectonic movements in the bedrock to explain these depressions. It does seem a bit poo-poo.
That was what was nice about having the if you like, the contemporary glaciology come, with the experience that the Quaternary sedimentologists had, that they'd seen these landforms in contemporary environments and could start to then, describe them in terms of how they were happening in the present, and then we could then start to interpret them of what they might look like as a legacy, as a relic landform. So that was the nice link of the working party, that we had that current research, that current body of knowledge, that current understanding, and guys who'd gone and seen these landforms and deposition environments in the field, where we were interested in them as a relic form in terms of ground engineering. They were able to bring that to the working party, and hopefully that's been distilled into the report.
Any more questions? All right. Thank you very much, David. Got a little present as an appreciation of...
I might not get on the train home, is it? It's got a cork in, it's okay, it's safe. Thank you very much, it's very kind. Thank you. Lovely, thank you very much. Thank you. Thank you.
Well, thank you very much all for coming here today, and hopefully see you at the next event.
Thank you for the invitation.